All right, today we're going to dive into two totally different tech worlds that, believe it or not, secretly power pretty much everything you do. We're talking about embedded systems versus data engineering. Let's get into it. I know, it sounds like a riddle, right? On one hand, you've got this incredible piece of 1960s engineering where every calculation was literally a matter of life and death. On the other, you have this gigantic, ever-changing system that's just trying to handle an absolute tidal wave of information. What on earth could possibly link those two? Well, the answer is that they represent two core pillars of our digital lives. One is built to live deep inside the machine, close to the metal, where it's directly controlling the hardware. And the other? It's built to manage that never-ending river of data that's constantly flowing through the cloud. So here's our game plan. We're going to explore these two pillars, starting by going inside the machine with embedded systems. Then we'll tackle that data flood with data engineering. After that, we'll put the two engineers side by side to really see the difference before looking at how they're actually building our connected future together. Okay, first up, let's zoom way in. I mean, we're talking about the hidden little brains inside almost every single electronic device you can think of. Welcome to the world of embedded systems. Now, here's the most important thing to get about these systems. They have one job, just one. Think about the tiny computer in your microwave. Its entire existence is about heating your food correctly. It's not surfing the web, it's not playing videos. It does its one thing, and it has to do it perfectly every single time. And, these systems have been around for a long time. The basic idea of a computer with a single purpose goes all the way back to code-breaking machines in World War II. But things really took off in the 60s with some mind-blowing engineering. And now these tiny computers are literally everywhere. The Apollo guidance computer is just the perfect example. I mean, this was one of the first real embedded systems, and the stakes could not possibly have been higher. It had the job of navigating a spaceship to the moon and back, all with less processing power than the calculator on your phone. It's an absolute masterpiece of specialized, super constrained design. And that really shows you the kind of pressure embedded engineers are under. It's this constant battle against constraints. The system has to be reliable enough to run for years without ever needing a reboot, cheap enough to go in a kid's toy, fast enough to react in milliseconds, and efficient enough to sip power from a tiny battery. It is an unbelievable balancing act. Okay, so now let's pull the camera all the way back. We're going from the world of a single microchip to the world of massive global data flows. Let's talk about data engineering. So, if an embedded system is all about one specific job on one specific device, data engineering is kind of the polar opposite. It's all about building the infrastructure, the digital plumbing really, to collect, clean, and manage insane amounts of data coming from millions of different places, all at the same time. And a really core idea here is this concept of data as a product. See, a data engineer's job isn't just to collect a bunch of data and let it sit there. Their job is to build systems that deliver clean, trustworthy, and easy-to-access data to the people who need it, whether that's a human analyst or an AI model. The heart of what they do is something called the data pipeline. So first, they have to ingest data from all over the place. Then comes the really critical step, transformation. This is where they take messy, raw, unreliable data and clean it all up. And finally, they serve that beautiful, high-quality data so it can be used to find real insights. Now, there are two main ways they build these pipelines. The traditional way is called ETL. You extract the data, transform it, and then load it into your storage. But the more modern way is ELT. You extract, load the raw data first, and then transform it. This is way more flexible because it means you can always go back to the raw data and transform it in new ways later on. So, what are the tools of the trade? Well, they're building all of this using some seriously powerful programming languages. SQL is absolutely king for querying databases, and then languages like Python and Scala are used to build all the complicated, automated workflows that keep that data moving and transforming. Okay, so we've met our two main characters, the engineer working deep inside the box and the engineer building the massive plumbing system for the cloud. Let's put them side by side and really break it down. So, the embedded engineer, their whole world is that intricate dance between the hardware and the software on one single device, and they're always fighting those physical constraints. The data engineer, on the other hand, is thinking about data flow at a massive scale, and their main battle is against data volume and quality. The analogies here are just perfect. One is like the device's hidden nervous system, and the other is the master plumber for a company's information. And it's so important to get this. Data engineers are the bedrock. Data scientists who are busy building the next great AI model, or the analysts trying to spot business trends, none of them can do their jobs without the clean, organized, reliable data that the data engineers provide. But here's the twist. As completely different as these two worlds seem, they aren't just running in parallel. They are deeply, fundamentally, and increasingly connected. And here's the punchline where it all comes together. Just think about the Internet of Things for a second. Your smartwatch, a connected car, a sensor in a factory. What are they? They're all embedded systems. And what do they all do? They generate tons and tons of data. Data that a data engineer's pipeline is specifically built to handle. You see? They desperately need each other. So you've got one discipline working at the edge, right there at the physical point of contact with the real world. And you've got the other working in the cloud, managing the absolute flood of information that the edge creates. You simply can't have our modern connected world without both of them. Which leaves us with a really fascinating final thought. As AI models get small enough to run directly on the embedded devices, and as the cloud needs faster and faster feedback from those devices, what happens to that line between them? Does it just disappear? That's the big question these two fields are going to be answering together for decades to come. Thanks for watching.